All right, we are testing. This is take one, test one of a Samsung phone to see if it works, because my other Samsung I had in the first half of the year kept going like this and I couldn't use it. That's why I had to use the iPod. I don't know if it's doing it right now as we speak, but maybe. Okay, now let's just go over something, a criticism Mustafa had. I don't mean that to sound as pejorative as it sounds, but it was a good criticism, but that it was a little confusing. For instance, the test was a little confusing or difficult because of the water and carbon tetrachloride. I'm not sure what you meant by that, but let's go over why something, first of all, like dissolves like. That's first of all. Second, it's a general rule of thumb. Things that are nonpolar, some things, can still dissolve in water. There's sometimes no rule. There's some things that are ionic. For instance, barium sulfate, calcium carbonate. They don't dissolve in water. Now, so then the question would be, is this one of your questions? How do you know something's nonpolar? Well, the way you know that is when we worked with molecular geometry. That's how you know. So you have to know what your shapes are. For instance, if I have carbon tetrachloride, the element with the most bond potential is going to probably be in the center. And if you have any kind of experience with chemistry whatsoever, carbon is normally, usually, all the time, probably in the center. So it's no great deduction that it would be carbon surrounded by 4 chlorines. Mustafa?
There's also 4 chlorines and only 1 carbon, so it's more...
Right, exactly. It's right. Simple deduction, understood. Okay, so here's what we have, right? Now, when you do this, you have to know whether or not there are unbonded pairs of electrons on the central atom. Why is that important? The non-bonded pairs the non-bonded pairs on a central atom is going to create a irregular geometry usually. Not always, but oftentimes. So it's important to know. Now, the first thing we do is we count the total valences, which means the total electrons in all of the valence shells of the atoms represented by the formula. So we know that there are 7 electrons in each chlorine and 4 electrons in the carbon, correct? So that's 4 times 7 is 28, plus 4 is 32. Now we subtract. We subtract off the bonded electrons. 2, 4, 6, 8. And that gives us 24. These are the bonds. And then what you do is you subtract off the electrons that complete the valence shells. Okay? Excuse me?
It's partly on the screen and partly off.
Okay, well, we'll try our best. This is a test anyway, Abby, but thank you for giving me an update on that. I appreciate that. So this is going to be complete the valence, and I'm going to put in 6, 6, 6, and 6, correct? That's 24 electrons. And then we're going to call that complete the valence. Okay? So that means that there are no more electrons to distribute around. So now you have to check things. You have to check to see that, 1, the central atom, if it's a non-metal, has at least 8, and it does. And you also have to check that each outer atom has 8 electrons, and they do, because you have 2 here, and then you have 6 additional ones that I didn't draw in, but I subtracted them here. 24, complete the valence electrons, correct? So now I know my dipoles are like that, but because of the orientation of the opposing dipoles, I know they cancel. So therefore, that is nonpolar. So given that definition, you would say carbon tetrachloride is not miscible, is not dissolvable in water. Now, there are certain organic chemicals that are very soluble in water. For instance, sugar, glucose, sucrose, fructose. Those sugars, those are sugar, and they are soluble in water. But how are they distinguished between sodium chloride, which ionizes, and the sodium and the chloride ions are solvated, surrounded by the water molecules relative to the orientation of the dipoles and the ionic charge, correct? So what's the difference between solubility of a seriously ionic substance, calcium chloride, sodium chloride, and sucrose? What's the major difference?
The difference is
yes.
One dissolves because it's polar.
Correct.
The other dissolves because it's ion.
It's ionic. Okay, fine. That's good, and I like that answer. Now complete it.
The molecules from the water surround the negative and positive ions from the glucose and sucrose or whatever that is, and they rip them apart.
Okay, so the water molecules keep hitting the sodium chloride, some kinetic theory, right? Yes, okay, from chapter 13 and 14, and then they're lifted up and solvated and they're suspended in solution. But what about the sucrose? Let me ask you this. This is important. This is a big concept in solution chemistry. You ready? This is big. Now, sodium chloride dissolves and the ions are solvated, correct? Yes. So therefore, the sodium chloride will conduct a charge, correct? Right? Now, sugar dissolves, but is it ionized?
No.
No, it's not ionized.
So it doesn't conduct a charge.
It doesn't conduct a charge.
It has carbon.
It has carbon in it, it has oxygen in it, it has polarity, and that's why it can dissolve. But the major distinction between a salt such as sodium chloride and sucrose is that
One is an electrolyte and the other isn't.
one's an electrolyte and the other one isn't. But being more specific is that the sodium chloride ionizes and sucrose doesn't ionize. Right? So that's the big difference. And that's in a very, 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 sounds easy, but believe me, it's big. In solution chemistry, it's big. Just because something dissolves doesn't mean it ionizes. But if something dissolves, it has to at least be polar. That's the lesson. Okay? Now, what I want to do is, and I'll make this ionic versus polar dissolving. Is that good? And now I'll come back and we'll do another one. I'll see how this turned out. And I want to find out what, given a molality, I want to know what the mole fractions are of the solute and solvent. Okay? Are you all right with that? Okay.